Talked about last class. Do you remember what we talked about?
Sets.
Sets. Very good. And what did we specifically do? We did two different representations of sets, right? And we saw that there are real trade-offs between the two representations, right? You could have either linear, or we could have constant quadratic. And what I wanted you to appreciate is that constant quadratic may not be the worst thing in the world. It really depends on what kind of task you're trying to use something for. And you'll run into this many times in your computer science careers where there's multiple different representations for a particular kind of data. And depending on what job we're trying to do, one representation may make more sense than the other. And as I said, in real systems, when you engineer real systems, you even will transform from one representation to the other as, for example, you see that your tasks change. Okay? The common thing that happens is what's called maintaining a journal or maintaining a log, which is just keeping track of all the things that happened. And for those things, you really want to pay as little as possible because you're processing transactions at a very high rate of speed. And so you want constant time addition in those cases. And then when you want to process the data, if the data processing is rare, maybe you don't care, and maybe if the data processing is more frequent, you then pay the price of transforming from one representation to the other. And often, when you build a real system, it's actually even more complicated than that. You won't say, oh, I'm going to wait. So remember, we had the with duplicates representation, right? Constant time addition, quadratic time. But it was actually bad because it was not quadratic in the size of the set. It was quadratic in the size of the representation, right? With all the duplicates, which could be really bad. So what you will actually do is often you'll say, look, yeah, I don't need to look stuff up very often, but when I do, I'm going to really hurt. So I am going to periodically cleanse this data set. Okay? Every time the representation set gets beyond a particular size, I'm going to go through and weed out all the duplicates. I don't know, 1,000 elements, million elements, billion elements. Really depends on the size of your processor, how long you can afford to wait, and so on. But when it gets to that size, I'll keep track of how many elements I've got. When it gets to that size, I will go and sweep all the elements, cleanse them, and now I have like this nice compact representation. So I'm paying a quadratic over a bounded size, right? And so I can actually do I would do experiments literally with a stopwatch, right? Or maybe not a stopwatch, but a computer stopwatch, right? It doesn't matter, you can use a stopwatch too if you like. Nobody even has they don't have a watch, nobody has any. Oh, excellent, well, congratulations, good, I love you. You can do an experiment and you decide, look, my quadratic over, say, 1,000,000 elements is fine. My quadratic over 10 million elements is fine. My quadratic over 100 million elements, I can start to feel the slowdown, right? And so you figure out your threshold, and then you do your cleansing run the moment your set gets to whatever that size is, right? And if it turned out you had lots of duplicates, now you get a tiny set. If you had relatively few duplicates, then you get a pretty large set at the end of the cleansing. But now you continue on with that cleansed set instead. Does that make sense? This is the kind of thing you do when you build a real system. Some of you I know have already done that. Some of you have not yet done that. And when you do that, these are the kinds of trade-offs that you'll run into. Okay? And by the way, I'm a big fan of reading this. It used to be the case that 10 years ago, this sort of stuff was just folk knowledge. It's still folk knowledge, but it's pretty public folk knowledge. There are some very good blog articles. Engineers at companies or just developers do fairly good blogs. Some of them turn into tech talks, and you're very lucky to be at Brown because they'll actually fly all the way to Brown and give you a talk about it just to try to recruit you to come work with them. But even if you don't go to the tech talks, there are some pretty good blogs. It's not like there's one blog. I wish there were, the one blog of awesome engineering posts. There's not. But if you follow, Twitter and things like that, you will actually come across a fair number of these blog posts. And those blog posts have a lot of really good insight into the difference between the algorithms of the textbooks and the algorithms that you use in the real world, and how there's a pathway from here to there. It's not like you throw all these out, but there's a pathway in the application. So I just gave you, the 5-minute summary of one such blog post. I don't know if it's actually a blog post, but it should be, right? This is the kind of thing that you can read blogs about that will teach you quite a bit. So Don't think you'll learn all of your computer science from blogs, but don't dismiss the blogs either. There's a lot of really good insight there. Okay? Questions about this? Any questions about what I've talked about so far, like yesterday's class and today's? Any thoughts, concerns, experiences, anything like that? Good? Should I go on? Okay, good. So, we gave two representations, but let's be honest about it. They both kind of suck, right? Because you have to pay a quadratic cost in one case, but even a linear cost. Now, if you think about it for a moment, linear, like how can you beat linear? You can't really beat linear, right? I mean, I want to know whether something is in a set. I gotta look at the set. I mean, you can beat linear pretty easily. I can give you a constant time algorithm, right? It might have a certain weakness, right? It might lie. So if you care about a correct algorithm, it seems hard to beat linear. And in general, it is hard to beat linear, right? You are going to have to look at every element of the set to figure out whether the thing you want is there or not. That's just, there's no choice about that. But, turns out we can be clever. And if you remember the recurrences that I gave you, I should briefly showed you in class and told you to go read in the textbook. Those recurrences, there's actually some recurrences that are better than linear. In particular, there's one recurrence that's really nice. It's better than linear because it's the logarithmic recurrence. Right? The logarithmic recurrence works by subdividing the problem into halves at every time. So instead of just removing one element every time, which is what we do in a conventional recursive walk, we're going to get half a subproblem on each subcall. Okay? And if we can get a half subproblem, it's actually a little more than that, right? It's a half a subproblem plus a constant amount of work. If you do a half subproblem plus a linear amount of work, you get the n log n recurrence. But if you do a half subproblem with a constant amount of work, now you get a logarithmic running time. Logarithmic's really nice, right? In fact, logarithmic is amazing because if you have a ginormous data set, logs, people familiar, like you studied logs in high school, do you feel like you really feel a log? I mean, not like log, right, rolling logs, but like a logarithm. Hey, let me give you. If you've never felt completely comfortable with logarithms, let me give you a simple, mathematically reasonable way to think about them that will make intuitive sense. Okay, logarithm of a number is essentially how many digits the number has. That's it. Okay, you can skip all the fancy definitions. That's really the intuition. Okay, it's a little imprecise, obviously, because 9999 and 10,000 are adjacent to each other, and their logs are adjacent to each other, but the number of digits is seems like a big difference. But essentially, that's what a log is. How many digits does something have? Okay, what that means is so I'm taking base 10 logarithms, right? If you're talking about decimal representations, if I multiply something by 10, I go up by only 1 in its logarithm. If I multiply something by 100, I go up by only 2 in its logarithm. If I multiply something by 1,000,000, I go up by how much? 6. Very good. Okay. And if a billion, I go up by 9. Good. So, what that says is even as the size of my data set gets bigger and bigger and bigger in big ways, the logarithm gets bigger in very small ways. Right? If I have a logarithmic algorithm and tomorrow, my startup goes viral and I get 1,000,000 times as many customers, right? I won't pay 1,000,000 times as much to Amazon's web services to process their data. I will instead pay 6 times as much, right? Which is much better than 1,000,000 times as much. So that's the intuition for a logarithm. Right? If you're a mathy person, you can think about it and you'll say, oh, I see the connection. If you're not a mathy person, logarithms may be a little abstract. You might think, I don't really get what's going on. I understand, like, oh, it's the inverse of some exponential it's like a fixed point thing for derivatives and so on. But this is really the intuition. And that's why, now you understand why it's useful too, right? Because I just turned it into hard cash in terms of Amazon processing costs. And if somebody pays Amazon processing costs, I'm very, very obsessed with this issue. So, we would like to get the logarithmic recurrence, but there's a problem. To get the logarithmic recurrence, we have to throw away half of the data. Well, it's easy to throw away half the data if you don't care about correctness. It's a bit harder to throw away half the data if you do care about correctness, because you're basically saying, I'm going to throw away data that I haven't even looked at. Think about that. That's a bit weird. Okay? Let's just take, I'm just going to take the simple problem of doing is in, right? And you can generalize from there. Simple problem of is in. I'm going to throw away half of the set without even looking at it. That should strike you as a little weird. If you had high school CS, you've probably been acculturated to not thinking of this as weird. I encourage you to get out of that shell and start thinking of this as weird once again. Okay? Because it is weird. How can I say something about values that I haven't even seen? Okay? It actually depends on something that's a little subtle. So I want to spend a minute or two talking about that. To be able to do that, we need to somehow be able to represent our data in, well, I need an ordering on my data. Okay? I need to somehow be able to talk about my data being ordered such that I can say, you know what, this datum that I'm looking for, it falls here in this order, and based on where it falls, I can skip the rest of the order. Okay? So I need a way to think about representing arbitrary data in some ordered way. Now, there's lots of ordered data sets in the world. In reality, there's only one we care about, which is numbers. Okay? So I need to take any datum I'm given and think of it as a number. Now, this is very easy for one particular data type. Numbers. Okay? So if all I have is a set of numbers, you can start to see how this might work. What I'm going to do is I'm going to have a representation where all of my data in my set are somehow put into an order, and then I can skip the ones that I can do some comparisons and whatnot. Okay? We'll talk about that. And then I have to think about the question of how do I turn everything else into a number? So let me talk about that for a moment. How do I turn an arbitrary datum into a number? Well, can I turn a string into a number?
Yes.
How can I turn a string into a number? Can I turn new hands, new hands, new hands, new hands, new hands, new hands? Any new hands? New hands? Just don't try to think about the here's what I'm going to do. I want you to spend about 10 to 15 seconds just thinking about it, because if your answer is yes, then probably you know the answer from somewhere else. I'm more interested in whether you can figure this out for yourself. Okay? So think for a little while. I'm giving you a string and asking you to turn it into a number. Okay? And I'm going to point out there are some questions that nobody is asking, which worries me a little bit. So, what could you do to turn a string into a number? Thoughts? Thoughts? Yeah.
String to code point.
String to code point. What does that produce? Produce a list of numbers, not a single number. Aha. But that's a starting point. Can we turn a list of numbers into a single number? How would we turn a list of numbers into a single number? Yeah.
I think you could sum them.
You could sum them. There we go. Great. Okay. So I have a string. I'm going to turn it into a list of code points. Okay. And then I'm going to sum those numbers. And now I have a single number representing that string. Okay. Does that or does that not produce a number? Okay. Based on the questions that you have asked me so far, we're done. So what's a question you might want to ask me?
Does each string need to have like a unique...
Ah, thank you. Okay, so that's the question nobody asked me before you started giving me answers. You didn't ask me for any properties of this. You didn't ask me, given a, two ways to put this, right? Given a string, does it have to have a unique number? Another way to put it might be, given a number, can I get back to the string that it started from, right? Can you give me, so we already have a candidate. Given a string, I'm going to take it, convert it to a list of code points, and sum those up. Are there two different strings that might produce the same number? Yes. Give me two strings that produce the same number if you're that confident. Who can give me two strings that produce the same number?
BA and AB.
Perfect, AB and BA, okay? So, AB and BA are going to produce the same thing. Well, so what else could we do to turn a string into a number? We can't sum them, apparently. Could we multiply them?
No.
We can multiply them. What else could we do? What else could we do?
Like take the numbers and just like squish them together.
Yeah, oh, so that's right. We can actually treat the numbers as a string, effectively, and concatenate all of those strings, right? And treat that as one giant number. So essentially that's equivalent to multiplying and adding, right? I mean, that's essentially squishing. Yeah. Okay, we're good with that?
No, because in that case, how do you differentiate between the single digits and the
So what is 110? Is that the same as 110?
You can make everything
Can you use
So we have to pad out all of the digits. We can do that. I'm going to show you a cooler idea. Okay? So, this is the heart of... And Kurt Gödel came up with this. It's a really cool idea. Okay? So let's take our string and let's turn it into code points. Okay? So we've got a string, and what we've essentially done is we've turned it into code point 1, code point 2, code point 3, and so on. Okay? And we need to turn this into a number. So what Gödel said is, here's what we could do. We could take 2 to the power of C1, 3 to the power of C2, 5 to the power of C3, and so on. Okay? We're going to take the prime numbers. It doesn't really matter which ones, but you know, for parsimony, we can take the prime numbers in order starting from the smallest, and just treat these as exponents. This number is actually a unique representation for the original string because of
fundamental theorem of arithmetic.
the fundamental theorem of arithmetic, which says that given a number, it has only one prime factorization. So we take some giant number that comes out at the end, okay? And if we refactorize that number, it's going to turn into some set of powers of 2s, 3s, and 5s. There's only one way that can happen, and so from that we can uniquely recover C1, C2, and C3. Okay? So this is called the Gödel numbering. Okay? And it's one of the multiple ideas that is at the heart of what's called Gödel's theorem. Someday I hope you take a course, if you haven't had the good luck yet, I hope you take a course in college where you learn about Gödel's theorem. It's like so astoundingly beautiful. It's completely useless, actually it's pretty useful, but you can think of it as completely useless and still just so astoundingly beautiful. Okay? So you learn about Gödel numbering as a trick in Gödel's theorem. Okay? So there is now a way to represent strings as numbers. Now, what happens if I have other data types? Like, let's say I have a pair of things. What could I do with that? Well, what I've actually shown you is a general technique for any sequence of things, right? So if I have a pair of things, I can just think of that as 2 to the Gödel encoding of the first thing, 3 to the Gödel encoding of the second thing, right? Recursive Gödel encoding. If I have an object, well, I can order all of the fields alphabetically and Gödel encode those in order, right? So we can start to play this game where we can start to build up more and more sophisticated things, and we can generate bigger and bigger Gödel numbers. Yes?
Can computers like handle?
Well, that's a different question. That's a different question. Well, actually, I mean, we saw Pirate can handle pretty big numbers. Racket can handle pretty big numbers. So yeah, if you're using a bad language, not my problem. Right? Okay. So of course, in reality, nobody in their right mind is going to do Gödel numbering, okay? Because it's computationally ridiculously expensive. So it's just a theoretical idea. It's just a way of making sure that such a thing can exist. Okay? I'll get you in on a secret. What we actually do is we don't use Gödel numbers inside our runtime systems. That would be painful. God. No, what we actually do is basically every object sits at some point in memory and we just use its memory address. Okay? Because the only thing I care about is that I have a unique way of going between the number and the value. Okay? It doesn't actually have to be in some alphabetical order, right? If I give you the points 1, 2 and 2, 1, like as 2 points in the plane, which one is less than the other? It's not even a well-defined question, right? But it doesn't actually matter. All that matters is that when I try to I can put all the points in order. So if I decide that this is equal to 2 to the power of 1 times 3 to the power of 2, and this is 2 to the power of 2 times 3 to the power of 1, right? What is this number? This is 3 3s are 9, 2s are 18, and this is 2 2s are 4, 3s are 12, right? And so this tells me that apparently this one comes before this one, right? This number comes before this, right? And that's all I need. I just need a way of putting them in an order in a way that I can recover later on. That's all I need. It doesn't really matter. It's a completely artificial, made-up order. Okay? Even for an actual number, there's no reason I have to follow a numeric order. It just happens to be a sort of natural thing. If you have to debug your program, it would be really weird if the numbers were all out of order, right? So for some data types, we'll take the value itself and other, or strings, you can use lexicographic ordering on strings, right? But for arbitrary data types, it doesn't really matter. So it turns out memory addresses are a perfectly good ordering technique. Okay? And I'm not going to talk more about memory addresses this semester, but they're just like where in the computer is your datum. Okay? Actually, we'll talk about them once in November. So. Okay, so far so good. So we have an order on our data. What that means is given any pair of data, we can now ask the question, is this datum, quote unquote, less than, equal to, or greater than this other datum? Why am I saying quote unquote? What's the scare quotes for? Yeah, because it's in this arbitrary ordering, right? Which could be like memory address ordering, right? It's not, is it actually less than? I'm not actually claiming that this value is somehow less than this value, right? It's not less than in a mathematical sense of like, I got a well-defined order that makes some semantic meaning. It's just less than under an arbitrary order that is reliable, that has this one-to-one property, right? That's all I need. Yes?
So if you're using something like memory addresses, so the whole point is that you can do like an is-in function. Like, how do you know that if two strings are like the same, they're stored in the same places in memory? I'm
going to duck that point. I'm going to talk about compound data, and I'm going to duck that question for now. Okay? Yeah. When we get into memory, we get into interesting questions about memory representations. I really don't want to do that here. Okay? So I'm going to assume that for okay, so let's not get into that. That would be at least half a lecture. Okay? Yeah. Okay, so here's what I've got as a result of this nice diversion here, right? You can use, certainly if you use Gödel numbering, there's no problem. So I encourage Gödel numbering at all times. Okay? Okay, so here's what I've got. I've got my set of data, right? I've got this universe of data, some subset of which I'm going to be asked to represent. And for each thing, I have some way of giving it a number, right? So it's now an orderable entity. So what I'm going to do is I'm going to put these numbers into trees. So now we're back to Friday's lecture. Okay? We're going to put these numbers into trees, and it's conventional to use binary trees. It's not actually a strict reason we have to, but it's pretty conventional to think about binary trees. So I have some value over here at some root. I have value on the left, and I have a value on the right. Okay? Yes?
You have two VRs.
I do indeed. What, you can't keep track of which VR is which? Okay, all right, fine, if you insist. Okay, thank you. Okay, so, value at the root, value on the left, and a value on the right, okay? And this might, of course, be itself another tree, and another tree over here, and so on. And I'm going to take the rule that the values on the left all the values here are less than the value at the root, where less than is in this funky ordering, right? This completely artificial ordering, right? It's just that I need a reliable way of getting a number for a value such that I can compare it against the number for B root and say, is it less than, then it goes here. If it's greater than, it goes there, right? So in this particular case, I erased it, sorry. This tuple would be on the left of this tuple, okay? Question?
I think we're missing that equality.
We have to think about equality for a moment. Next question.
If you
No, we'll get back to that. Sorry, I'm not ducking it. Yeah.
if your algorithm that you're using to sort things into the tree.
I haven't talked about it. We haven't written any algorithms yet. Okay? We're just talking about the data structure representation. We'll come to the algorithms, and I'll take algorithm questions after that. Okay? Yeah, no algorithms yet. Okay, so what about equality? Why did I skip equality? It's ternary, right? And I've got two things. What about the third one? Yeah.
Doesn't really matter, just we only care about whether it's in the, like if something's equal, we can just,
Well, if it's equal, it is the root.
yeah.
Right, so that's implicitly what's going on, right? So if a value is equal to the root, it is the root already, right? So because we had that, right, uniqueness of mapping. Yeah. Okay, there was a hand up in the back somewhere. Somebody had a hand up. The same thing? Good enough? Okay, good. Okay, so this is going to be our data structure, okay? So we need to generate a computer representation of the data structure. So here's what I want you to do. I want you to spend a minute with your neighbors. Remember, introduce yourselves. Spend a minute and give me the data definition. Because this is just pictures on a board. I need to actually represent this in this particular case in Pirate code. So I need a data definition in Pirate that represents these trees. Okay, go.
Oh, so that's like going It wasn't an empty case, it was just you had an empty list. What do you need value?
I want you writing code, by the way, not drawing pictures in the sky. You can draw pictures here, but I want you to write code too. I'm going to ask you to read out code.
I saw this.
All right.
Like some nodes in your spreadsheet.
5, 4, 3, 2, 1. We're back. Okay, so what I would like is I would like first your simplest representation, okay? I don't want the most complicated representation we can get. What I would like to do is I'd like to again continue going in groups. Are you all sitting relatively similarly to who you were sitting with before, or not even remotely? Good, that's fine, great. I'm glad to hear that. You're meeting new people. So I guess I can still pick up where, what I would like is I would like the person who didn't talk last time, if possible, to try to talk this time, okay? I would like all of you to get comfortable talking in class and, you know, making mistakes. I make mistakes myself, so we all make mistakes. So let's try to do that, okay? How about we start, where did we let off? Somewhere around there, right, last time? How about we start right there? Go. Do you folks have a representation you want to try out?
Sure.
Great.
So we said like the data tree. Colon, there are two cases.
Hold on, so let me write it all down. Okay, two cases, okay, fine.
So the first one is just, it could be empty.
Okay, I'm not going to use EMPTY because it's already taken, but I'll use my favorite way of writing empty. Okay? Okay,
Like
yeah.
Tree, just like lower to tree.
Yeah,
and
yeah.
then left.
Uh-huh.
And like the double colon tree, comma right, double colon tree.
Okay, great. Excellent. Okay, next pair. Well, let's go that way.
We did.
Hold on. We're going by pairs. We're not back there. We're going this way, right?
Sorry.
Actually, yeah. Sorry. We're going this way. This way. Yeah. Do you know actually there's a name for going in this order? So if you go like this way and then you come back around that way and then come back around that way and you go back around that way, you sort of do this thing. It's called. It's called Boustrophodonic. Boustrophodonic actually is a very meaningful.
Can you please spell that on the board?
I'm sorry, yeah, I'm not sure I can, that's why I'm just yelling it out. And it comes from Boustro, which means ox.
That's so true.
That's how oxes go plow a field. Boustrophodonic. Okay, good. So, with that, with your little humanities lesson for the day, let's move on next group. Yeah.
So we said something similar, except we did, so rather than doing empty, we said a tree could be either like a leaf.
A leaf.
Have a
Okay.
number, sort of in it.
Okay. I know. I'll do it again. Leaf.
Yeah.
Okay. And
Yeah,
leaf
we
had
said-
what?
We called it a root, which is like a number,
Okay. R, which is a number.
or it could be
Are you okay with this? Good enough? Okay. Next group.
Oh, okay.
Next pair.
Okay, so we said like close to the first one, so we have the empty case, but in the second case, there's also a root.
So in this case, so you had an empty, but then you had a root. Okay, so you had an off. Thank you. Okay, that was a little unexpected. Okay, and you had a number. Okay. Okay, so we've got three candidates. We've got the black tree, we've got the green tree, which has the R and the empty, and then we have the blue tree, which is a leaf along with the black part over here. Okay? So, now, would anyone like to, let's vote on these, okay? So we've got the all black tree, that's vote number 1. Vote number 2 is for leaf over here and the black part over here. Vote number 3 is for empty over here and the green over here. The green plus black over here. Okay, so how many vote for the all black? Nobody. Oh my God. Okay. How many for the blue version? Green version? Wow. Okay. That was unexpected. What do people not like about the all black version? Somebody new. Yeah.
There's no value.
Yeah, so the all black version is perfectly fine except for one small problem. It sort of forgets to put a value someplace. We need a place to hold on to a value, right? Otherwise we can't actually record any of these values. So good. All black version's a bit problematic. Okay, how many of you seem to... So what's wrong with the blue version? Blue version.
Because the leaf doesn't have the left and the right like a tree, so it'd be difficult.
Yeah, so it's hard. The problem with the blue version is if we don't have a value to compare against, like our tree, it's like we don't have a thing to compare at the root, right? Remember we said there's going to be a value at the root, right? So there's no value at the root basically, and it'll turn out that it'll make our algorithms much messier. So the version that I use in the book is this version. I use an empty for the leaf, and I have a value followed by a left and a right tree. Okay? Questions about this? Let's first understand this definition. Questions about this definition before we get back to dealing with more issues here. Question, yes?
Yeah, is it bad nomenclature to call T like a node instead?
Yeah. So I would use slightly different names, but yes, I'm not picking the names here. I'm actually going to change all the names. So almost all the names. Yeah. There was a hand up over here. Yeah.
In this case, wouldn't you, like, every tree you have to have a value even if you don't want it to have, like, anything coming out of it? You just assign?
Aha! So, what does this force us into trees that we might not want? So construct for me a tree. Let's do this. Let's draw a picture of a tree that you think is not easy to represent here. Or that you don't want to have to represent.
Okay.
What's a picture of a tree?
So, like, you have the root vertex, and that's the only one you want.
You want, and so it's got some value, maybe 5 or something like that. And that's the only thing that's the whole tree that you want to represent. Is this a tree that is difficult to represent in our representation? No?
Oh, yeah.
Why not? Why not? Well, how would you represent this? Yell out the code to represent this. So this is equivalent to this. So yeah, it doesn't say empty, empty over here, right? But it's morally equivalent. Okay? So this is, by the way, this is a very good question because visually there is a small difference between these two, right? Like this one says empty and just the circle 5 doesn't say anything about its children, but because it's a tree, in our representation, if it's going to have a value, it must say something about its children. It's perfect. However, it is justified in saying its children are empty. That's how we're going to represent, right? This picture demands a representation. We have a representation. It may not be your perfect representation or ideal representation, but it's a reasonable representation. Okay? Next question. Okay, good. All right. So, I'm going to use slightly different names over here. I'm going to call this BT. I'm going to call this a node. And a BT stands for a binary tree. It's brown. We don't make judgments, but our trees are allowed to be binary. Okay? So, we have a binary tree. It's either an empty tree, meaning we have no information to represent, or we at least have a little bit of information to represent. Here's the real thing, so especially slightly more mathy people, but everyone really should learn how to think this way. Here's the real question you should be asking yourself, like one of the sanity checks of a representation like this. Do I have the ability to represent every possible size of tree? Do I have the ability to represent a tree that has 0 information in it? How? Empty. Do I have the ability to represent a tree that has 1 unit of information in it? Yes, excellent. Thank you. Thank you. Perfect answer. Pointing at the board was the right thing to do. Okay? Do you have the ability to represent a tree that has 2 pieces of information in it?
Yes.
How many different ways are there of representing that? 2 ways, right? Either a left child that has data or a right child that has data. 3 pieces of information. How many ways of representing that are there?
4.
Something like that. Yeah, it starts to grow. Okay. Yeah. Well, we'll actually get to this question of how to represent, how many representations are there around November 10th or so. So it's actually some fun math behind it, but I'm not going to go into that now. So the point is, we should ask ourselves, can I represent all of those? That's a good litmus test, because if I can't even do that, then clearly my data structure is broken. If I can, then maybe I can do it, maybe I can't. Okay? All right, good. Now, our BT representation lets us chop out half the data on every recursive call. Right? Well, actually, does the data type BT let us do that?
No. Like, so if you had the list, like with like, just like the first node.
Hold on. We don't have any lists here. We don't have any lists.
That's right.
The point is our data type, does our data type let us ignore a child on every recursive call?
No.
Our data type does not let us do that at all. The data type representation we've written over there does not actually correspond to this. It doesn't say anything about the values inside the subtrees at all. Okay? It says nothing about the values in the subtrees. So, how can we change our data type to actually reflect that? Is there something we can do to change our data type to reflect the fact that we have something that is called a binary search tree? This thing is called a binary search tree. A binary search tree is one where this property holds. Recursively, everything on the left is less than the root, everything on the right is greater than the root, and that holds for the subtrees as well. Okay? That's a binary search tree. That's the thing we need before we can go throwing away half of the nodes or throwing away a subtree in our search process, right? In our subset search process. So, what could we do to make this binary tree into a binary search tree? Any thoughts? Yeah.
Have the qualifier on L and R that they both either have to be empty or the value of L has to be less than the value of the
How do I write that?
the percent thing.
Yeah, we're gonna have to do a percent thingy, okay? So the simplest thing to do is actually to say data BST is equal to a BT percent is a BST, right? That's essentially what we're trying to do. Now, do you think you could write the predicate is a BST? What is a BST? What's the signature? What's the type of is a BST? It's a function that consumes BTs and produces booleans. It produces true precisely when what? Yeah. Point. Exactly. That. Okay? Precisely when that is true. You think you could write that predicate? I want to hear a resounding yes, absolutely, not a problem. Would you like it right now?
Yes, absolutely.
Yes, I would. Go. Oh, that was a trap. Never fool you that way again. Damn, shouldn't have used it. Yeah.
Shouldn't be left included only have a single value, like all values?
They're trees. They're trees. They're trees. They're whole trees.
But each one only has a single value.
No. So
The data tree.
there's a root for that, and its root needs to be less than, but then all the elements in it also need to be less than. Okay, this is great. This is great. This is great. This is great. Okay. All right. So I know you all can. Let me ask you the following question. Here's a question. It's a fun question. I can think of two different ways of defining is a BST. Okay? One is, given a root value, I can check that every element on the left is less than the root value, and every element on the right is greater than the root value. Right? That would require traversing the entire subtree to make that one check. The other thing I can do is I can simply check that the root of the left, so basically I can look into the left side, right? And it's either going to be empty or it's going to have a node, right? If it's empty, I'm done, obviously, because everything in there is less than, because there's nothing there, okay? Or it's a node. So the node has its own root, right? So I've got a node, I've got V root over here, and I've got V left root over here, and it's got some subtrees over here, right? So, much simpler, much more efficient thing I can do is simply check that V left root is less than root, and recursively, this is also a binary search tree. Okay? And similarly, I've got a V right root, and it's got some children over here. So I check that V right root is greater than V root, and recursively check that this is a binary search tree as well. Okay? So, two processes. First process, check the entire left subtree. That's terrible, right? You can imagine I'm just traversing this tree every single time. Second one, simply check the roots and check that they are then recursively binary search trees. Okay? Talk to your neighbors for 30 seconds and tell me which one you prefer. Go.
One thing I'm kind of writing is how you feel like you have to case, right? I guess it's up Oh, that's what it is. Well, actually, no.
In 5, 4, 3, 2, 1. We're back. So we're going to vote. We have a choice between the efficient process, okay, and the slow process. So how many of you choose the efficient process? Good. How many of you choose the slow process? Okay, that was unexpected. Why would you choose the slow process? Slow process? Slow process? Slow process? Really? Why?
Because let's say v root is about.
Give me an example, because it
Yeah.
sounds to me like you have a counter example in mind to the fast people.
Yeah.
Okay, good.
So let's say v root is a value of 5, v left root is a value of 3, which still holds that it's a BST. However,
Definitely. Okay?
However, its subroot, let's say, has a v right root of 6. That doesn't hold with the v root of 5.
There's your counter example. Right? So if all you did was check the root node, that doesn't tell you that this part is certainly a binary search tree, but this whole thing is not a binary search tree because this now is bigger than 5, and so it's no longer the case that everything in the subtree is less than. Okay? Yeah. Ooh, sneaky, I know. Okay? So you actually have to check the whole thing, and this is why you don't actually want to write that code. I mean, it's good to write the code, it's healthy to write the code, but you don't want to write that in your program because every time you run it, it's going to be doing this deep recursive check on everything. Okay? So I write it when I'm testing, and then once I'm done testing, when I deploy, I take off the check because it actually destroys the algorithmic complexity, right? You have to look at the whole tree, and the whole point is we're trying to build an algorithm that doesn't look at the half the tree, and so that would be kind of self-defeating. Okay? All right, good. Now, with this, with a proper BST, assuming we have proper BSTs, on every recursive call, we get to throw away one whole child. We compare against the root, and if it's equal to root, we're done. We found it in the set. If it's less than, we go into the left subtree. If it's greater than, we go into the right subtree. And so we're done. We've gotten our logarithmic complexity. Right? Good? Okay, great. So, next class, we'll pick up on a new topic. See you next class.